Now we turn to section 2, which gives a refresher of part 1 of the Webtalk 4 analysis, continuous outcomes. So on slide 14, we list 3 different models. We're going to call them dynamic models, meaning that, as in the first case, y2 is regressed on y1, y3 regressed on y2, etc. That is, you have direct regression relationships between the y's of the observed outcomes. Here you have a lag 1, auto regression lag 1, because y3 is influenced only by y2, not by y1. You can add a random intercept to this model, and that's denoted by the circle I, random intercept, influencing the outcomes in addition to the autoregressive feature of order 1 that you have here. And you can even have a more advanced dynamic model where you have a so-called ARMA model, AR standing for autoregressive and MA standing for moving average. And for instance then, y3 is influenced first of all by I and second of all by y2, but is also influenced by the residual of y2. So the deviation from the expected value from I predicting y2, that deviation influences the next outcome. So this is just a repetition of what we talked about in part 1 of Webtalk 4 for continuous outcomes. On slide 15 we have a totally different model. We still have a random intercept, but the autoregressions are not among the y's, but among these latent variables, which we think of as residuals between what's predicted in y by I and the actual y value. And what we've done in the past then is to create so-called within level factors here. So that has to do with the variation across time, whereas the random intercept factor is between level factor, representing variation across individuals. These factors influence the y's without the residual. The residual is 0. If it's not 0, you can think of it as a measurement error, but that is typically hard to estimate. Or models like that have various kinds of convergence problems. We rewrite this model, as we discussed in part 1 of Webtalk 4, in the new Mplus fashion, where instead of introducing factors, we talk about the residuals right away as their own quantity here. It is a latent variable in the sense that it's not observed, but we just refer to it as, say, y2 hat, and draw it like this without having to specify a w y1 measured by y1. Now the RI-ARMA modeling is the univariate part of RI-CLPM, so that's for one of the 2 variables, and then you have relationships between the residuals here of one process and the residuals of a second process. Cross-lag panel modeling does not include the random intercept I, so it's using the AR1 model on the previous slide here, which is then quite different in that the dynamic relationships are for the observed variables. Turning to slide 16, the paper by Asparahov and I in 2022, the residual SEM paper, introduced a new model, RI-ARMA, which is similar to the previous slide, the top model on slide 15, the way of writing the model using explicit factors defined as f by. Here we have that same setup, and we have the regression relationships on the factors, for the factors, instead of between the y's. So it has the same spirit as the RI-AR model because of the separation of between and within individual variation, which by the way is also referred to as latent centering, or centering using the latent random intercept I. But we add an MA, a moving average component, so we have once again the third variable being influenced not only by the second, but also by the residual here. So we have this jagged figure. Now there is an equivalent measurement error version of this, RI-ARMA, measurement error autoregressive, where these zeros are actually estimated parameters instead. But it's also a little bit tricky to estimate, and we're not going to focus on it here. On slide 17, I show correlation plots for the RI-AR1 model. They will look a little bit different for RI-AR2 models or for the RI-ARMA model that we're going to talk about later. But here it is the simple RI-AR1 model. So we're going to see how the random intercept and the other regressive coefficient impact the correlations. So what we're looking at here on the x-axis is time points 2 to 10, and we're looking at the value of the correlation between time point 1 and time point 2, time point 1 and time point 3, up to time point 1 and time point 10. So we have 4 different curves here for different autoregressive coefficients. And we also have 4 panels depending on what the RI variance is, or in the metric that we're talking about, that's the same thing as the R square in the outcomes for the due to the random intercept. So 0, 0.25, 0.50, 0.75. And we see that in each case, the lower limit for the correlation is the same as the R square. 0 here, 0.25, 0.50, and 0.75. Here's a fairly common situation with the random intercept contribution R square of about 0.5. And we see then that the correlation between the first and second time point has a contribution above that by 0.75, for instance, in the autoregressive coefficient 0.5 case. And actually this follows a simple formula for the correlations using psi as the random intercept variance and beta as the autoregressive coefficient. If you look at time point 2, the correlation between y1 and y2, then you have beta to the power of 2 minus 1, so that's beta itself. So the contribution here above the random intercept contribution is beta times 1 minus psi. And beta is 0.5 here, and psi is 0.5, so 1 minus psi is 0.25 as well. So the product is 0.25. So 0.5 plus 0.25 comes up to 0.75. And you can test that for the other cases as well. This formula is a simplification of formulas that come from the AR1 literature, but they turn out to be the same when you restrict the variance for the random intercept to give certain R square values. So we're going to have this picture in mind when we look at real data and plot the correlations across time. And again, the correlational contributions will be different for different models, RI-AR2 or for RI-ARMA. RI-ARMA, for instance, has a longer lasting correlation across time beyond on top of the random intercept contribution. Okay, on slide 18 then we get back to the combined data, from the first data set, and look at the stress and alcohol risk outcomes. So up at the top here you have the means of the stress variable over the various weeks up to week 16, and where 0 means the baseline week. So we after treatment starts at week number 1 here. And we see a slight decline over time, which at first we're going to ignore and then pick up on towards the end of the Webtalk. And in the bottom part of the slide, you look at the proportion of individuals who are abstinent, and none of them is abstinent at baseline. They're all alcohol users. But right after the baseline, you have, when the treatment has started, you have a much higher proportion of abstinent people, and drops down a little bit at the second week, and then you have a slight decline of abstinent people across time. At first, we're going to ignore these trends over time, but pick up on it in the modeling towards the end of the Webtalk. So the combined stress outcome is quite well measured across the time point in the sense of coverage. That is, proportion of the data that's not missing. So here we're looking at weeks 1 through 16, that is, in this case, 8 occasions. Week 1 is what we're going to call Y1, up to week 16, which we're going to call Y8 for simplicity. And here you have the Mplus output for the coverage of those different time points. So 0.817 says that 81.7% of the people have data on Y8. That is, they don't have missing on that. So that's a fairly good, very low attrition rate, fairly good coverage at the last time point. And then we also want to look at covariances between Y7 and Y8. 0.71 says that 71% have data on both Y8 and Y7. So fairly good bivariate coverage as well across time, which is important when we look at cross-lag modeling. So that's something you want to check early on. If you have a lot of missing data, low coverage here, you become more and more dependent on missing data theory and the assumptions underlying that theory. And if you have a lot of missingness, you may depend more on modeling assumptions than your data, which is obviously not a good situation. Here's what the average correlations for the stress outcome looks like as a function of the time distance. So on the x-axis we have the time distance in weeks. So with week 16 we have a time distance between the last and the first of time point of 15. So this is the correlation, the first value in the previous correlation plot that I showed you earlier on slide 17. So that correlation starts at a little bit above 0.7, and it goes down to a little bit above 0.5, which would suggest that we have a fairly high random intercept variance of 0.5 and maybe a medium auto-regressive coefficient of the difference between these two, namely 0.25. Very similar to the bottom left correlation graph on slide 17. Now this plot, of course, is in terms of observed values, not all having the same trustworthiness. For instance, for the last point, you only have one correlation that has the time distance of 15. That is between week 1 and week 16 in that case. So here you have the number of correlations at each time distance in weeks. Says that you only have one at 15, a distance of 15. In total, there are 28 correlations. 8 times 7 divided by 2. So you could, if you want to, and I know that Ellen Hammacher is fond of doing this, plot each correlation here, so you have a scatter plot of several correlation across time. So this plot suggests a high RI variance and a sizable auto-regressive coefficient. On slide 21, I show the results of the analysis of stress using maximum likelihood. So here we have a series of 9 different models, and I want to remind you that outputs for all the models are posted on the website of the talk. So the first 6 models are of a kind where the dynamics, that is the relationship between variables across time, are for the observed variables, whereas for the last 3 models the dynamics happens for the residuals. So it's quite different models. So first we have the AR1 model, which gets a very poor fit, p-value clearly 0 here, but also very high chi-square and poor RMSEA with a very low probability of it being less than the 0.05 threshold, probability being 0. Even the CFI is poor. Adding then a lag 2 part to the model, we have some more parameters. The log likelihood improves, it gets less negative, and BIC improves, it gets smaller. And chi-square drops from 700 to 200, still fairly poorly fitting model. Now you can take the approach of ARMA, that is an autoregressive moving average model. 1, 1 here means that it's autoregressive of order 1 and moving average of order 1. You have the same number of parameters as the AR2 model, but the likelihood is much better, and for the same parameters, number of parameters, and therefore the BIC is much better. And here we now for the first time see a positive value in a p-value 0.2432. So quite a distinct difference between model 2 and model 3 here for the same number of parameters. And the RMSEA is good with a high probability 1 of being less than 0.05 and a perfect CFI. Now we can add a random intercept to these models. A random intercept to model 1 gives you 1 more parameter, 24 instead of 23, and log likelihood is better. It's not as good as the ARMA model. The BIC is better than the AR models, but not as good as the ARMA model. And the chi-square then gets a p-value of 0 here. And you can add a second lag 2 model to this random intercept model for the observed variables, and you still have a p-value of 0 here. And you can even try an ARMA model with this random intercept, and then you get a decent p-value, but you get a negative insignificant variance for that random intercept. Now when turning to the last 3 models, you have then the dynamics between the residuals. So you have a separation of within and between person variation. Now the AR1 model still doesn't fit. It is, however, significantly better than the AR1 model. Adding 1 parameter, the random intercept, chi-square drops down from 700 something to 72. So we're clearly in a better ballpark here. Adding a lag 2 to that model, we get a p-value that is greater than 0 at least. So that's a reasonable model. The RMSEA is low, a high probability that's less than 0.05, and a very high CFI. So that shows that there's a real difference between AR2 models and RI-AR2 models. Now in terms of bringing in moving average components, model 9 is then of interest, and that's the new model that was introduced in the Asparuhov-Mutén paper 2022, which will appear in the SEM journal. So it has the same number of parameters as the RI-AR2 model, but it has a better log likelihood and therefore a better BIC. And here then we get a very good chi-square, p-value 0.3616. Chi-square drops from 33 to 15. So that's a very, very nice model. So we're looking at it again on slide 22, and you have the figure up here. So we have in Mplus language, we have the model for the measurement of the random intercept with fixed loadings 1, so it's a true random intercept up here, which influences the observed y variables. But now we take the tack of putting within level factors behind each variable with residual measurement error 0. And for those variables, we have an autoregressive function and also a moving average function with this jagged development across time. Sawtooth style. So we create all of these 8 factors f, and then we say that the measurement error is 0, measurement error variances are 0, and then we do a regression f2 on f1, etc. up to f8 on f7, which is the autoregressive part, and then also f3 on f2 hat, which is the moving average part, up to f8 on f7 hat. And we note that we do not regress f2 on f1 hat, because f1 hat here is the same as f1 because there's no other variable influencing f1, whereas for f2 it's influenced by f1 and the residual, so f2 is different from the residual, but that's not the case here. So we do not say f2 on f1 hat because it would be the same as f2 on f1. Now the reason we go to factors here is more of a matter of Mplus language. The f factors, as I say here at the bottom, they could be replaced by y hat, but then we would need y double hats or something else for the moving average parts of the f3 through f8 pairwise on f2 hat on f7 hat. So just for language matters more than anything else, we are still forced to create factors like that for RI-ARMA. On slide 23, then we have the estimates for the RI-ARMA model using maximum likelihood estimation with robust standard errors and chi-square. The first thing you want to look at is whether or not you have a substantial random intercept variance. Here the estimate is 3.9 with a standard error of 0.9. And we know that we don't want to look at a z-score because we're testing at the border of the admissible parameter space, namely 0. And instead we want to, we're not getting into how to test that, but we're going to instead require that we have a fairly healthy ratio, say a ratio of 2 or 3, to conclude that the random intercept really needs to be in the model. In some cases, for some outcomes, you will find that the random intercept estimate is no larger than its standard error, and you may consider then dropping the random intercept. It may not be important, perhaps not important for this type of outcome to have a trait, but then you revert back to an AR model. That is, in the cross-lagged situation, you revert back to a CLPM model instead of an RI CLPM model. In this case, you will revert back to an ARMA model. The standardized estimates are interesting for the random intercept as measured by the 8 y variables. The raw coefficients are fixed at 1. Standardized coefficients give you information about, say, the correlation between the first and last time point due to the random intercept. So that's the first standardized loading times the last, which is 0.428. The total correlation between time 1 and time 8 is higher than that, 0.539, as it should be, because you have a certain contribution from the autoregressive and the moving average parts, even at that time distance. You can also look at the importance of the random intercept in terms of the R square in the observed variables that it creates. So the observed variables as a function of the random intercept. So for y1 here is then simply the square of the standardized loading, 0.452. So that is a very high R-square, of course, and signifying that the random intercept is important. And it's about equally high throughout the 8 time points. Just square those coefficients. Looking in the right column, you have the dynamic part of the model, where we regress 1 time point on the earlier time point. And here you see an autoregressive coefficient correlation of about 0.5, which is then in line with the correlation graph on slide 17, bottom left situation. Now here it's a little bit more complex because we have an MA, moving average component also. So for F3, we have F3 regressed on F2 with a high positive coefficient, but we also have coefficient for the regression coefficient of F2 hat, the residual at the previous time point, which is negative. So here you have a pattern which is commonly seen with MA models, where the residual contribution has a negative sign, saying that F3 is dependent not only on F2 but also on the residual at F2, so that if the F2 residual is specifically high, especially high, then the F3 value will be lower because of it, the negative coefficient. And the fact that you have negative throughout here then invites mirror modeling, MEAR, that is measurement error modeling, where there is a certain equivalence between this model, RI-ARMA, and a measurement error version of it, as discussed in the Asparov-Mutien 2022 RSEM paper.